Okay, now the streaming is started. Okay, the topic, yes, we were talking about the thermal properties of the matter, and thermal properties of the matter is basically divided into three further parts. One of them is the thermal expansion of the solid, the second one is consequences of the expansion. Basically, this is entirely the same one. Then we will have the specific heat capacity topic, and then we will be talking about melting, boiling, and evaporation. Okay, so when we talk about this topic number one, that is actually the thermal expansion. So what does it mean by thermal expansion? What do you think about that? Yes, right?
So when the temperature increases, the volume of the
Yes.
substance also starts to increase.
Perfect. So that starts from that discussion of that assumption that volume of the substance increases as the temperature increases, right? Volume of the substance increases as the temperature increases, right? What are the reason behind that? The reason behind that are there are three types of substances, basically matter, sorry, solid, liquid, and gases. So that is why if we think that the temperature change is only in solids, or in liquids, or in gases, so it is not true. But in all these, the temperature increases due to different reasons, right? Sorry, volume increase due to different reasons. So here we go. We will be talking about linear expansion as well as volumetric expansion. So there are two aspects of this. Linear expansion, or you can say the volumetric expansion. So linear expansion is change in length. Change in length. And what about the volumetric expansion? The second expansion is your volumetric expansion, and volumetric expansion is change in volume. So actually, what happens? Change in volume takes place, but we simply say, for oversimplification, we say that length changes. But as I told you, that what happens? In fact, volume changes. Now, when the volume changes, we will consider that, okay, what happens in solids, what happens in liquids, and what happens in gases. So, beta, in solids, how the volume change takes place, the at higher temperature, the molecules vibrate more vigorously. That is why what happens to those molecules, the intermolecular forces between the molecules get weaker, and their intermolecular distances increases. Do you get this point? It is very simple logical explanation that at higher temperature, the intermolecular distances increases in the solid. Okay, so at high temperature, at high temperature, the molecules or the atoms, you can say, atoms of solids vibrate vigorously. One thing, and the their intermolecular gets weaker. Okay, what is the third aspect of that? Due to that, their amplitude of vibration increases, right? Their amplitude of vibration increases. Okay, amplitude of vibration of the molecules increases, and that's the reason of the increase in the volume, so that their volume or length increases, so that they expand. Is it? So they expand. Is this clear to you? Any question
Yes,
or
sir.
any query related to this? So in solids, if I just tell you, for example, if there are the atoms in the solid, like these are the atoms, these are the atoms, I will just show you a linear uh, change in the atoms. Actually, in atoms, the molecules are related with each other, or molecules are connected with each other in such a way that they are attached with the help of a spring with each other. So, what happens when this spring, when the molecules attach with the spring, they are compressed and then they are, this is basically the normal temperature. So, what happens when the temperature increases, the molecules they get up, yani these molecules move apart from each other, right? In this way, when they will move apart from each other, did you notice that basically their temperature, their length has been increased? Did you see? Their length has been increased. So if you increase the temperature more, the length increases more. So in this way, the molecules expand and expand and expand. So is this clear to you all? These are the atoms. So I have just shown you a simple mechanism of atoms. These are the atoms. So this is at lower temperature, lower temperature, right? At temperature increased, and this is high temperature. You got the point? Is this clear to everyone?
Yes, sir.
Okay.
Yes, sir.
So basically, this is how the volume of the size increases. But remember one thing which is very uh, easy to understand, that in solids, the expansion is least. Okay. In solids, the expansion is least. They do not have much more expansion as compared to that of, as compared to liquids and gases. Okay, it is clear to you? Now we have the second type of substance, that is the liquids. Because in liquids we have more expansion than that of the that of the solids. Why? Because the liquid molecules are arranged in the form of group, so their molecules, yani the liquid molecules, their molecules already have already have weak forces, right? So at higher temperature, what happens? Again, at higher temperature, you can say, or as temperature increases, the liquid molecules, or the liquid molecules move apart from each other. Liquid molecules move apart, okay? And when they move apart, their volume increases, so that their volume increases. Is this clear to you? Their volume increases. Actually, in liquids, there is very interesting mechanism of volume increase. I'm gonna show you that. First of all, for example, if I have a flask like this, although this is not a symmetric flask, but okay, let me draw it for you. If I have a flask, that conical flask, or something like this, that conical flask, and that flask is uh, that includes some liquid inside, okay, and along with that, it has an opening here, and in that opening, I have placed a sort of, yeah. Now, did you see this flask ever in chemistry lab?
Yes, sir.
Yeah, this is called a round bottom flask or a conical flask. Okay, now I have a question related to that. Now, this flask is placed on a heater. It contains some liquid inside. Now, this is basically this flask. Uh, initially that flask is cold, and when that flask is cold enough, then that flask is, this is that flask. Okay, this is, unfortunately this flask has changed the color. Anyhow, no issue at all. So that means that if you have some liquid inside, for example, the level of the liquid in this flask was this one. This is the level of the liquid. Let me call it point A. And this was the entire liquid in this flask. So when this flask is being heated from a burner heating source, what happens? It expands, right? What happens? The flask expands. I have shown you that flask. Yes. Now the flask has expanded, and the flask expands. What do you think? What will happen? The liquid volume does not change, huh? So that will come down here. Now this is the volume of the liquid. Yani, this is now position B. You got my point? You are still hitting this. So actually here the flask expand, right? Flask expanded. And on the third stage, what will happen? The liquid will expand and its level will increase again. So this is very important thing to understand, that now not only the flask expands, but the liquid expands right now. Okay, so that is why at stage 3, the volume of the liquid increases again, and this liquid reaches to a new position. Let's say this is the position C. So this is your position C. You got my point?
Yes, sir.
Okay. So actually, what happens? Uh, the initial stage, the liquid had this level. Finally, the liquid has this volume. Yani at intermediate stage, and finally the liquid has this volume in this stage. So, what is the actual expansion in the liquid? Is it from B to C, or A to B, or A to C?
Sir, B to C.
B to C. Well done. This is basically, this is uh this is A, this is C. So there are two expansion levels in this equation. So A to C, sorry, A to B, then B to C, and then A to C. These are 3 points what I wanted to explain to you. A to B is basically expansion of flask. Am I right? Expansion of flask. So that is why liquid level decreased. Okay. From B to C, B to C, the volume of the liquid expand. Yani it is actual expansion. Actual expansion of liquid. Okay. It is actual expansion of liquid. Okay. Now from A to C, it is apparent expansion. Remember, this is very interesting thing. Apparent expansion. Apparently, you will see that, oh, I have placed the liquid till point A, and now it has reached to point C. So it is called apparent expansion. Okay, is this clear to you? Any question till this point?
No, sir.
Okay, so this is very rare question. It is asked to you, but it is a complicated question. I mean, most of the students are not able to answer this. So here there is a point that in liquids the expansion is usually uh, more than those of the solid. So I will try to write that point at the top because I don't have space below. I don't want to extend it by this page. So liquids have more expansion than solids, but less than gases. Agreed? Are you people agreed?
Yes, sir.
Okay. Now there is the last entity, which is basically the gases. So in thermal expansion, the third, participant is the gases. In gases, they have the highest expansion. Yani, the gases have the most expansion, or largest expansion. Okay, and what happens to the gases when you increase the temperature? Their volume increases, right? We have studied that in detail. As temperature increases, as temperature increases, volume of the volume of gases increases. So when volume of the gases increases, at that time you can say that yes, the gases expand. Is it? We agree? So also the gas expand. Now the expansion of the gas is infinite. Remember this thing. The gas has infinite expansion. It depends upon the volume of the container. Infinite expansion. Okay? Its its expansion depends upon what? The volume of the container. Okay. So volume of container. As volume increases, the pressure decreases. Do you agree with all these points which I have actually discussed before? So gases have no intermolecular forces, but at higher temperature, at higher temperature, the molecules of the gas have very high kinetic energy so that they move very far from each other, right? At higher temperature, what happens? Actually, this is the deeper level question. At higher temperature, the kinetic energy of gas molecules is very high, so they move very far from each other. So the molecules move far away or apart from each other. You got it? And this is basically a consequence which will take place in our thermal, the exchange, thermal exchange. So I will discuss that over there. So hopefully it will be helpful for you in that point or at that point. Okay. Any confusion till this point or anything you want to ask me about the thermal expansion topic? Yes. Nothing.
No, sir.
Okay. Now we will be talking about the thermal, everyday life, daily life examples of thermal expansion, right? Daily life applications, daily life applications, or you can say the application areas of your thermal expansion. Yes, who is with me in the class? Irtuza, Ibrahim, Muhammad, and Raib,
Yes,
all of
sir.
you? Okay, okay.
No, it's like
So
last year, sir.
okay, the class will be right at this time, inshallah, daily. So please try to avail the time here. Okay, so application areas are, for example, in thermal expansion, there are so many examples of solids thermal expansion in your daily life. For example, one of them is, yes, one of them is uh, the railway tracks. Okay, we have these uh, applications of the solids in our day. Yani, you know, we place some gaps between the railway tracks. Uh, for example, this is a railway track. I will try my best to draw it. Oh, yeah, it is fine. So, what happens to that railway track? This railway track will be basically, yeah, there would be some gaps between these railway tracks. For example, if these two are the railway tracks till this point, okay, then we will draw the railway tracks next to it here. Now you have some gaps in between. So these gaps are basically placed in such a way that in summer, what happens? The metal expands, and when the metal expands, they must have a sort of mean gap between them. So that is why usually these tracks are carrying some gaps. So if they will not have gaps in the summer, what will happen? They will overlap each other and they will be damaged. Okay. Then there are some other examples, so many examples. For example, okay, let me write about this a little bit. The gaps are placed between the tracks to prevent any accident in summer, as the metals have expansion, as the metals have expansion, so they will cover these gaps. Okay, they will cover the gaps. Otherwise, otherwise the tracks will bend and can cause damage. Okay, actually, this topic is almost qualitative analysis. That is why I'm trying to make it as qualitative as required. Now, in the winter, there are so many applications. I can give you a lot of applications. In the winter, sorry, there are some. Did you see the wires are some sort of the poles which are basically damaged during the winter, the broken poles. Here we have the poles, and there is a electric wiring between these poles. These wires are there. So these wires are basically placed in such a way that they are kept a little bit sagged. Why? Why? Yes. Can anybody tell me? These wires are put a little bit loose. These are the loose wires. So in winter, the electric wires, electric mm, high voltage transmission, high voltage transmission lines, high voltage transmission lines have a sag or sags, especially in cold areas. Why? In winter, the wires contract. Actually, if you see the broken wire in the snowfall, they are not broken due to the load of the snow. They are basically broken due to the contraction. You got the point? Wires are broken due to contraction. Is it clear to everyone?
Yes, sir.
Okay. So we keep them a little loose, yani we keep a space for them to be getting, a little bit contraction. Then the third is the riveting. Okay. For riveting, when you are going to rivet two metal plates, like for example, this is a metal plate, okay, and you want to join it with another metal plate, okay, like this. Then what happens? We rivet them all. This is one of the metal piece girder. This is the second girder, metal girder. And what do? We rivet them because these are the metals. So how will they be stick together? We put hot rivets inside them and hammer the rivets. Okay, these are the hot rivets. We put the rivets, and what do? We just hammer these rivets, and when we hammer these rivets, actually, these all rivets are fixed here. This is the riveting method. Did you see these riveting rivets anywhere? Yes. So these rivets basically they're hot, and when you hammer them, they have a maximum length. So when they get colder, what happens? They contract, and while they contract, they fill these gaps. Yani, these gaps will be now filled. There will be no gap here. These gaps will be now filled. You got the point? Is it clear? Should I write something about that, or is it clear?
It's clear, sir.
Okay. Then the fourth application is basically the rims of wheels, wooden wheels. Usually, the rims of the wooden wheel are uh, supported with the metal ring outside, right? This is a hot metal, and inside that metal, there is a wooden ring. For example, these are the wheels of the buggy. Did you see the buggy? The cart? Hmm? Yes, we have seen it. हाँ भैया इतना था. Did you see that? Cart देखा है? The horse cart. This is that type of setup. So, you know, what do we do? Hey, just a second. Okay, sorry, sir. Now, this is a wheel, and it is basically it has the rims outside. So when it has the rims outside, basically this wheel will be having a sort of, sorry, yeah, when it will be cold, it will shrink it, and it will basically keep this inner wooden rim enclosed. So that will help us out. Then fifth application is basically your bimetallic strip. Okay, bimetallic strip. So, beta, bimetallic strip is that type of device which is used in electric temperature sensors. I will explain that in detail in my next class. Used as an used as a temperature sensor in electric devices, right? Temperature sensor as a thermostat, as a thermostat. I will talk about that in detail. So I hope that this thermal expansion topic is to somehow clear to you. So do you have any question till this point?
No, sir.
Okay. See you then, inshallah, in the next class.